Hello everyone. We already started our demand prediction project with the series and we already finished two stages, which is how to take the data, how to clean the data, and then in the second stage we have already gone through the feature engineering and visualization. So the third stage is petrol demand forecasting using SARIMA, which is SARIMAX, which is a time series forecasting model, as well as one of the deep learning important complex pattern prediction, which is long short term memory using a deep learning method with some KPI analysis, key performance indicator analysis. So that we are making as a stage 3, which is building the model and also analyzing which is best model in that. Okay, let's start with I already executed, so I'll just show you how we have done what we all taken the tools and skills required for our notebook, which is Python notebook. So started with the libraries like Pandas is important, then NumPy, and then Matplotlib for any visualization under this. And the main is the one of the important first model we have taken as a SARIMAX, which is autoregressive integrated moving average with the exogenous factor with seasonality. So this is a extension of ARIMA. ARIMA was a base model. Okay, so Sarima is with seasonality, we can predict the model. Okay, so to import that Sarimax, we are taking it from the main model, which is stats model, which is a statistical model building the this particular model from .tsa because it is a time series analysis, and the state space because from the dot state space we are taking this Sarimax as a dot Sarimax. And as usual, we need a min max scaler before going for the long short term memory. We need to scale the data. So for that, we are taking from the sklearn dot pre-processing, import min max scaler. And then to evaluation purpose, we are taking a sklearn from matrix, import mean squared error. And we can take a root mean squared error. Many more are there. Matrix, you just go through that, which fits better, you can take it. And just I'm showing one of this as a demo. And then from the TensorFlow.Keras.models, I'm importing the sequential. This is required for our calling our LSTM. Okay, on top of TensorFlow, we are taking the models with the Keras. And from TensorFlow.Keras.layers, we are importing LSTM as well as dense layer, which is required for the output purpose. So these are important libraries we need to take before building the model. Okay, and you already know in the stage 2 we already made cleaned data to the feature engineering and also some visualization that we have saved as a petrol feature stage 2 that we have just taken into my Colab environment. That as you know, in these files you can just directly upload. Okay, and take it into your place. That's it. I've already done, just I'll show you. You know how to read it, pd.read csv of the whatever the path in your environment, that you can copy path and save it. And just I'm taking now what we have: date, product id, product code, warehouse, product category, order demand, whether the store is open or not, whether there is a promo or not, state holiday, school holiday. And we already extracted the some features in the feature engineering, like a day of a week, is weekend, whether quarter, and lag features like lag 1, lag 7, lag 14, lag 30 by shifting the lags like 1, 7, 14, 30 days, and rolling mean average of the last 7 days as a rolling 7, rolling 30 as a last 30 mean average, and EWM as a exponential weighted this moving average of 7 days. So that all we have extracted the features which is required for our time series forecasting. That is important demand forecasting with our petrol. Okay. So let's start with our building the model. Model one I'm taking as, I'm just showing only two models. You can take many more models are there, but I'm considering the SARIMAX and LSTM is the best suited model for demand forecasting, as we are predicting with the time series forecasting as well as predicting with the complex pattern. So I have took the LSTM. SARIMAX is a seasonal autoregressive integrated moving average with exogenous variable. Like it extends the ARIMA by handling seasonality and allowing the external variables like exogenous inputs. And it combines both AR autoregressive differencing and moving average components as we call a PDQ, okay, in the short form. It is ideal for time series forecasting with repeating seasonal patterns and making the factors which is influencing, and it provides some interpretable parameter, what we call it's explainable, and works well for the small to medium sized data set. Okay, if you want to have some explainable answer to the clients, the SARIMAX is the best suited. And if you have a long time dependencies and the very complex patterns, then LSTM is best suited. Okay, so let's start with that, how we can take the SARIMAX forecast. We'll call for SARIMA order as 111. As I said, it is a PDQ, AR term, integrated term, and MA term. These are important component parameter which is required to understand how model can build the model. Okay, and also SARIMAX, which is with the seasonal order as well. So we are taking with 1117. 7 is a one seasonal term. 7 means weekly seasonality. 7 days we are taking into place here. And how to call that SARIMAX model? We'll take one variable as a SARIMA model equal to SARIMAX, which is already taken imported as a SARIMAX from the Statsmodel TSA state space dot SARIMAX, which is inbuilt, and we'll call that functions now SARIMAX with a parameter df of order demand, so which is our target order demand, and order we call a SARIMA order. Okay, and also seasonal order, as it is seasonal order we have taken, and enforce stationarity equal to false means we are not making any enforcing the stationarity as a false. Okay, if it is there, that also be accepted. And also inverse invertibility, if it is there, that has to be accepted, so we are initially making it as a false. And we are calling SARIMA results equal to this SARIMA model dot fit, means we are fitting the model with a function dot fit. And DISP equal to false means we are making that anything whatever we called invertibility, stationarity, so the anything is there, so that should be acceptable, so we are taking it as initially false. And then how to forecast it, I have already executed, so I am not executing again. Okay, and how to forecast it, just call n forecast equal to 30 if you want to make a next 30 days. Okay, if you want to make 7, you can take next 7 days, like that. And SARIMA forecast you are calling with this SARIMA results dot get forecast is a method to forecast, get underscore forecast with the steps, how many steps you want to take, like a n forecast, like 7 days, 30 days. Here we have taken 30, so we are taking a 30 steps to forecast in the next forecasting the parameter values. So SARIMA predict we are taking as a SARIMA forecast, whatever we are get the forecast dot predicted mean value of it. So this is how we can make it a forecast. So coming to the model 2, we are taking LSTM. Let me give you a brief about it. LSTM is a recurrent neural network, RNN. Okay, so it is on top of that RNN we have designed to learn a long-term dependencies in a sequential data. Okay, and it uses the gates like input gate, forget gate, output gate to control the flow of information across the time steps. Okay, what happens in the RNN, we were not having some information mechanism such control gates to take care of a long time dependencies, information to be taken into the place, which information to be forget, which information is required to be moved forward. Okay, but that is mechanism is held by LSTM, so this has been built on top of RNA. It is excellent for a non-linear data as well as complex time series forecasting task. It performs well on large data set. As I said in the previous SARIMAX, it works well on medium sized as well as small size data set. But here LSTM works on large data set. Okay, and also capture both short to long term patterns effectively. Only that purpose we are using deep learning. there will be a deep learning effectively making our building the models to learn lots of things. Okay, let's see how to do that. First, we'll make some feature engineering for LSTM. Last in the feature engineering I have shown you, but again I want to showcase once again. Lags I have taken 1, 7, 14, 30. The last lags of some list of the lags, and I'll make it as a for lag in lags. Okay, data frame of f lag of lag, because each lags it has to go through the loop. So df of order demand dot shift of lag. Whenever I take a 7, it should lag 7. If whenever I take a 14, it should lag 14, like that. I'm taking one example, df of rolling mean, which is 7 mean of order. Okay, so I'm taking a df of order demand dot rolling of 7 dot mean. It's a meaning average of 7. Okay, and df dot drop n equal to in place equal to true. Okay, n is some not a number, it has to be dropped here. Okay, and this is very important. Before creating the sequence of the LSTM, we have to scale the LSTM, because it's very important. Until unless you are not scaling the LSTM before the building the model, you'll not get a proper answer. Okay, so scalar is very important in LSTM. So I'll call a min max scalar as a scalar now, and scale data we have to fit it as a scalar dot fit transform with a what target data, which is df of order demand. Once we have scaled, we'll go for the sequence creation of our LSTM. How to create it? First, we'll define the create sequences with the data, whatever data we have, and sequence length as 30. For example, next length I have to take as a 30 days. Okay, and initially I make an empty list of my x and y. X is my input, y is my target, which is output. Okay, and how I'll make a loop for it? For I in a range, sequence length, comma, length of data. Okay, then x dot append, x is my input, dot append data of I minus sequence length, okay, to I. Okay, and then 0. Okay, and then y dot append of data of I comma 0. Next, last value is my y, and x is my first I to sequence length. Like that, I'll be taking as my input and the target, and it has to be repeated until unless we'll get the next one. Okay, and return np is again, it is a numpy, numerical manipulations or numerical array type of whatever calculations comes, no, we have to use a numpy. So the shortcut name is np dot array of x, and np dot array of y is my returning value of input and target. Initially I'm creating the sequence like this, and then I made already sequence length as 30, and x LSTM y LSTM equal to create sequences of scaled data, whatever we have scaled data. Okay, and with the sequence length, this is the important parameter need to be taken in the creating the sequence for the LSTM. Okay, and then we'll split the train and test as integer of 0.8 into length of x LSTM. Means for the training data we are taking 0.8, means 80% of data we are taking for the training, and remaining 0.2, which is 20% of data we are taking for the testing. Okay, and it randomly takes the data. Okay, and we are calling x train comma x test equal to x LSTM of splitting. Initially nothing means starting index to the split means 80% of data, then comma x LSTM of split to split means 80% of data from there to remaining. Okay, that is obviously default 20% of data. Similarly for y train y test, y LSTM of first 80%, then y LSTM of next 20%, which is for the y test. Okay, this is initially how we can create the sequence for the LSTM modeling. And we'll reshape for LSTM, like a first it takes a 3D data. Okay, first it takes a samples, then it takes the time steps, and then it takes the features. These three data is required for LSTM. So how will you take x train equal to x train dot reshape, x train dot shape of 0, okay, then x train shape of 1, and then comma 1 as a one feature we are taking now. Okay, if you want more features, you can take more features as well. Like similarly for x test. And how to build a model, we have a particular method like LSTM model equal to sequential. First, whatever sequential we have imported now here, this one sequential. what we are imported from the TensorFlow.Keras.models, that we have to call that function before calling this LSTM. Sorry. Yeah. Yes, we are calling sequential. Okay. Then once we call that model, we are adding the layers. As you know, these are neural networks. We are calling the number of hidden layers to activate through the ReLU. Okay. ReLU means it is a rectified linear unit. Through that, we're having the activation functions, and through that, the hidden layers, we are going to the processing the inputs and getting the output as a in the dense layer. Okay. So how to add it that layers? LSTM model dot add, starting with LSTM of 50. Okay, these are units, 50 units. Activation equal to ReLU. Then input shape equal to, as we have a sequence length, comma 1. Okay, then we have to add the dense at the last, that is LSTM model dot add with a dense of 1. Only one layer is required for last one, dense. And LSTM model dot compile. Compile means before executing or before fitting, we need to compile it. That is, we have a different compiler with the optimizer. Optimizer means how we can optimize that compilation. We are using ADAM, adaptive model. Okay, that is important to optimize it. And we are talking the loss function as mean squared error. Okay, you can take a root mean squared error as well. Okay, we have a different metrics like evaluation for a regression type of project. Okay, then we'll fit the model as like we did with the SARIMAX. LSTM model dot fit with X train, Y train, epochs. Epochs is how many times you want to make the neural network to the go to each batches. Okay, so epochs equal to 20 we are taking, and batch size we are taking 32. Means size wise we are categorizing 32 sizes of batches. In each batch it has to go to the epochs. And validation split we are taking zero point 0.1, and verbose we are taking 1. These are important parameters required for fitting the model. Okay, I have already executed this. So how it executes? See, epoch 1, epoch 2, epoch 3, like the 20 epochs. Okay, and each epochs it takes batches of 32. Okay, and it how many time steps it is taking. Okay, and what is the loss function on each epochs, and what are the validation loss we got. Okay, that we are getting here, so that we can understand how many what's the loss functions we are getting. Okay, through that we are making how many times it is making the model to train itself. Okay, so through that we can get a proper value later. Then we can predict and inverse the scale. How to predict it? Y predict underscore LSTM as LSTM model dot predict of X test. This is a method to predict it. We have to take a X test now, not train, because we are predicting the next test 20% of the data. Okay, then Y predict LSTM equal to scalar dot inverse transform, because we already scaled. No, we have to take it to inverse the transform to have a initial values. Okay, so for that scalar dot inverse transform of Y predict LSTM, and Y test actually scalar dot inverse transform. Okay, with the Y test dot reshape it again, because we already reshaped 3D, and we again back to the 1, that is minus 1 comma 1. So this is through that we are getting 1058. Okay, in that we are getting 10-second time steps, that is 9 millisecond. Okay, so this is how we can inverse it. And model comparison, we are taking SARIMA comparison, takes last n test points. SARIMA prediction last like a SARIMA results dot get prediction. Start with the index with a df as a minus length of y test actual, and end with the df of index minus 1. Okay, this is a way of how we can get the predictions of n test points, and you can make the prediction last as SARIMA dot predict last as it is dot predicted mean dot values. We can have average value of a predicted. Okay, and RMSE calculation, which is a root mean squared error as a loss function. So RMSE LSTM equal to NP dot square root of mean squared error of y test actual comma y predict LSTM. This is a formula for root mean squared error, and we are calculating for LSTM. Similarly for SARIMA. Okay, then we'll print it both. We got something around for LSTM root mean squared error. Okay, we are getting 31718. Okay, and SARIMA it is 31676. Okay, And we are plotting this with the plt.figure with figure size, y test actual, y predict LSTM, SARIMA predict last, and petrol demand forecast, and time with the order demand like this. So we can say this is the order demand and this is the time with respect to that actual blue color, whatever it is actual, okay, values, and LSTM prediction is in orange. See, we are taking only one few points, and SARIMA we are predicting with a green color. This is just a visualization how it is taking almost near to that. Okay. And KPI calculations, it is very, very important in the client project, a key performance indicator. So inventory test, we have to make it. Okay, usually we'll be having in the data set inventory level, but I was not having in my data set. So instead of inventory level, I have took demand only with respect to the previous order demand, whatever we have, that we are calculating with the inventory test. If you have an inventory level, you have to take in the inventory test as a inventory level column. Okay, df of inventory level dot iloc, which is the index of that minus length of white test actual dot values as your inventory test. Okay, and price per unit, you can take a data frame of petrol price because you have a price dot iloc of 0. Okay, so each index it takes. Stock out and overstock, you have to calculate to understand whether in at what point of there was a stock out, or at what point there was overstock. So through that you can have a inventory management as well. Okay, so we have a formulas like a safety stock equal to zero point 0.1 into y test actual dot flatten means make it into 1D dimensional data, and stock out rate LSTM equal to np dot mean of y test actual dot flatten if it is greater than inventory test. Obviously stock out when it happens. Okay, if your actual whatever prediction, whatever you are making the demand prediction, if it is that is greater than inventory means, inventory means stock is less and inventory is less stock, and your prediction is more means obviously you are going into your inventory management as a stock out. Okay, rate you can make it as a into 100. Similarly, overstock means when it happens, your inventory test, whatever you have a stock in your business, which is greater than whatever you have test actual. Means test actual means whatever you are predicted the demand. Predicted demand, if it is lesser than the inventory, no, your stock, with safety stock also you can consider with your actual demand, then obviously it is a overstock rate. Okay, this is a way of taking the formulas to understand. And revenue growth also you can understand here. Y test actual demand prediction into price per unit with your whatever your petrol, whatever product you are taking. And revenue prediction, you can make a Y prediction LSTM dot flatten into price per unit. Okay, and revenue growth, you can take it as a revenue prediction dot sum, whatever you are taking, and minus revenue actual sum. Obviously, growth means whatever I predicted, that I have to minus by the revenue actual, and whole divided by revenue actual with the sum into 100. Okay, and inventory trend you can calculate as a inventory test dot mean minus y test actual mean. So this is a trend, you can test it, then you can print it that we got something around stock out rate at 3.7 percentage, overstock rate is no, 0 means no, so overstock. Revenue growth something minus 24.98 means it is a negative, no growth. Okay, like that with respect to your data set, your client data set, you can check it out. This is just for a demo, we have taken one data set, with respect to that we are showing it how we can predict it. Coming to the cross validation and hyperparameter tuning, no? Example for a SARIMA. Simple grid search method is useful, like a PDQ into PDQS. Okay, this is a like order with a whole seasonal order. Okay, first we'll make import iter tool means iteration tools, and import warnings. If you have any warnings, you can filter that like warnings dot filter warnings to ignore, and PDQ, whatever AR term, integrated term, and moving average as a range of 0, 2. We are making it as like that. And PDQ is a list of iter tools dot product of PDQ. So this is a method we can use for a cross validation and hyperparameter tuning to have a better performances. So that also I'm showing here. Best AIC. Best AIC means if you want to understand which model is best. So we have a AIC. AIC is Ekaiki information criteria. Through that we can understand which is best parameter. Okay, so we take best AIC is np.info. Okay, and best params is none. And for param in PDQ, for param seasonal in seasonal PDQ, we are going for try and accept method. Okay, in try we are making a model as SARIMAX with DF order demand, order as a param, seasonal order as a param seasonal, enforce stationarity and enforce invertibility as false, and then results as a this model dot fit with the disp as false. Okay, and if the results dot AIC, okay, is lesser than best AIC, then best AIC equal to results dot AIC. Like that we are understanding which AIC means best model. Okay, then we are confirming with best params as a param and param seasonal. And except for the errors, it has to go continue. Okay, and here print best params as a with AIC. Okay, so we are getting I can say here through this conclusion here, SARIMAX is best for short term, okay, stable forecast interpretability, easy to explain with the clients. LSTM best for capturing non-linear trends and long term dependencies. And KPI based evaluation helps to decide our model which is best for client purpose, for stock out, revenue, inventory optimization. Okay. So here we got best params as a Sarima params, none with AIC. Okay. It is none with AIC. So you can understand here. So we'll ensure some date column is date time then, and we'll go for next, and we'll get a last date, initially date, last date of our data set, and we'll future prediction will make a 7 days, okay, to showcase you. So n future will take initially 7, and future dates equal to pd dot date range from a start date is my last date, which is a maximum of our data set, and pd dot time delta of days 1 and period says n futures. Okay, and Sarima prediction data frame will take as a Sarima future df as a pd data frame, because we need to convert date as my future dates and predicted order demand as Sarima future prediction, and we'll print Sarima 7 days forecast as Sarima future df. Okay, we got is next 7 days forecast as per our previous data set. Okay, so previous data set was just 11th of 11 November 2024. From that onwards means 12th of November 2024 to the 18th of November 2024, we got a value of this. Okay, so we got a forecast values. Okay, that is 5764.458399. Okay, so this is our predicted order demand. Okay, so this is how we can have predictions of the Sarima. Similar way we can see with LSTM next 7 days. We'll make a last sequence at scaled data of minus sequence length last 30 days. And LSTM future prediction initially make empty list, and current sequence is last sequence dot copy, then for underscore in range any futures, predict LSTM model dot predict with our current sequence, reshape it as you know 3D data, one sequence length and one. Okay, samples, time steps and features, and LSTM future prediction dot append predict 00. Okay, an update sequence with np dot append current sequence of 1 to last, and 00 for prediction, and reshape for -1 1, and inverse the scale with the inverse transform with again np.array LSTM future prediction dot reshape it, and then flatten. Okay, and LSTM prediction data frame has LSTM future data frame equal to pd dot data frame, where we are taking date and predicted order demand as a future prediction. Okay, we're printing and we are getting next 7 days. Okay, so you can combine and forecast as a comparison, like this comparison df with the data frame date, Sarima and LSTM. You are getting, say, for next 7 days, Sarima prediction demand is this one, LSTM predicted demand is this one. Okay, and also you can take inventory and price assumptions, like inventory future is a repeat of order demand with -7 to last. Okay, and a per unit petrol price you can take, and safety stock Sarima zero point 0.1 into Sarima future prediction to take the safety stock, and for same for LSTM. And if you want SARIMA KPIs, you take SARIMA stock out rate, overstock rate, revenue. For LSTM, say thing stock out rate of LSTM, overstock rate of LSTM, revenue. Uh, these formulas remain same as we are seeing previous, but for the different model we keep the different models with formulas. Okay, and we are getting see here Sarima stock out with 100%, overstock is 0, revenue is something different, and here also revenue is different. Okay, some around Sarima is getting good revenue growth. Yes. Okay. Similarly, you can have a different with a different data set. Just I'm showing a demo how to use our model for the demand predictions, and then we'll visualize it with a matplotlib dot pyplot as plt. Okay, future dates with Sarima forecast, LSTM forecast, inventory level. Okay, so here you can see here, so this blue color is a Sarima forecast and this orange color is LSTM forecast, and this dot dot is inventory level. Okay, so inventory level is this, and your Sarima forecast and LSTM forecast is this. Means your demand prediction is more than your inventory. Means you're going to be stock out, obviously. So it is showing 100% stock out here. Okay, need to be improve our stocks. Okay, with respect to our data set, you can understand here. Okay, and Sarima is more explainable, and it makes for a small to medium level data set, and LSTM is good for complex patterns and big data, I can say large data set. Okay, so I can give you conclusion that you decide which model to use, like Sarima to be used when demand is stable or seasonal, and you want easy to explain forecast for the inventory planning to the clients, and you prioritize lower overstock rather than revenue spikes. Okay, if you want to choose LSTM when your demand is non-linear type of data and has sudden changes, if you have sudden changes in your data, you want to capture spikes and trends, and your prioritize is a higher revenue and accurate peak demand prediction, go for LSTM. Okay, rule of thumb is compare stock out rate and revenue. Okay, lower stock out plus higher revenue is the best model. Okay, lower stock out plus higher revenue is the best model. If both are similar, Sarima is more interpretable, that we can say it. Okay, I hope you understand this how we can petrol demand forecasting using SARIMAX and LSTM with some KPI analysis, and we'll go through next video with last stage how we can deploy the model with our Streamlit or a Flask, how we can make use of this all model to be with a dashboard presentation that we'll see in the next coming video. Thank you.